morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn about one of the topic in electromagnetic waves and transmission lines as UHF lines and followed by input impedance of a transmission line. So, firstly, we are going to learn about UHF lines. So, UHF stands for ultra high frequency lines. These are also called as RF lines, nothing but radio frequency lines. UHF lines are circuit elements for the transmission lines and followed by input impedance of a transmission line. We are going to learn in this particular lecture. Right? So, here ultra high frequency line, or in short we'll call it as UHF lines, ultra high frequency lines. So ultra high frequency lines are also called as RF lines or radio frequency lines, and those are commonly abbreviated as UHF lines, or one of the types of transmission lines. Ultra high frequency lines have operational frequency, means the range of the frequencies are to be in this particular lines. Ultra high frequency lines are ranging from 300 to 3000 megahertz, or wavelength is from 100 centimeters to 10 centimeters. Right? So generally this UHF lines are ranging from 300 to 3000 megahertz, mean 300 megahertz to 3 gigahertz, or wavelength is starting from 100 centimeters to 10 centimeters, right? So in general, this ultra high frequency lines or UHF lines are called as RF lines also. Under normal frequencies, the transmission lines are used as waveguides for transferring power and information from one place to the another place, or one point to the another point. At ultra high frequencies range, the transmission lines can be used as a circuit elements like a capacitor or an inductor. Right? It means that they can be used in circuits like a capacitor or an inductor. Right? That's why UHF lines as circuit elements as the topic we are going to learn in this particular lecture. So now to calculate the ultra high frequency lines as the circuit elements, based upon that input impedance calculations need to be performed. Now to perform all such calculations, firstly, what are the different fundamentals required to analyze this UHF lines? Now we'll see first, then we will move on to the mathematical equation derivation part related to that input impedance. So first, characteristic impedance. As we know that impedance is generally denoted with Z, and the characteristic impedance can be denoted with Z0. Now in that we are going to, so in order to calculate that Z0 firstly, so how the four primary constants of a transmission line are connected in the circuit. According to that means resistance R and inductance L are connected in series, whereas the conductance G and the capacitance C are connected in the parallel as a circuit elements V, and this is V0. Okay, so based upon these two series elements, we will be considering series impedance as Z, and based upon the parallel combination, will be considered the shunt admittance as Y. As we know that impedance Z and admittance Y are reciprocal to each other, or Y equal to 1 by Z. Right? Z is equal to 1 by Y, or Y equal to 1 by Z. Right? So series impedance Z is equal to R plus J omega L, which is equal to J omega L. Why? Because it is equal to J omega L, means since omega L is far greater than that of R, means this at high frequencies case, it should be, means can be neglected as with the power dissipation element as resistance. Hence Z is equal to J omega L. So according to the circuit elements, R plus J omega L is the equivalent impedance. Now according to this condition, if omega L is far greater than that of R, then Z is given by here j omega L. Then similarly, from the shunt elements, connection between these two G and C, or if you observe, two are connected in parallel and the connection is said to be shunt. So the parameter which we are considering from this parallel connection is shunt admittance, and it is denoted with Y. Y equal to which two are connected in the shunt connection? Conductance G and the capacitance C. Hence G plus j omega C equal to j omega C only. Why? Because here if omega C is far greater than that of G, then these two can be considered as Z is equal to j omega L, Y equal to j omega C at high frequencies. Why? Because ultra high frequency range means 300 megahertz to 3 gigahertz it will be. Frequency components are to be transmitted as large. That's why we are considering, if you consider the frequency components and the power dissipated elements are to be very, very less in the circuit. Hence, we will neglect R and G in the circuits. Then series impedance Z becomes j omega L and the shunt admittance Y becomes j omega C only. Right? Now, according to the characteristic impedance, Z0 is equal to root over Z by Y. Impedance to the admittance, which is equal to j omega L by j omega C. Why? Because from this series combination, R plus j omega L, and as we know that Z0 characteristic impedance is Z0 is given by, in general, all the primary constants equation, that is R plus j omega L by G plus j omega C. Now if we substitute, if we neglect R and G, then when compared to the omega L and omega C, then it becomes Z and then the denominator term becomes Y. Hence Z0 is equal to root over Z by Y. We can write here, then which is equal to root over j omega L by j omega C. Now, in the numerator denominator, j omega gets cancelled, which is equal to root of L by C. Z0 is equal to root of L by C. So, it is a purely reactive and there is no resistive components and is used as impedance matching devices. So, purpose of impedance matching is means to transfer maximum power from source to destination. We use the concept called impedance matching. Means there the load impedance and the characteristic impedance must be same. Then that is the case, maximum amount of power is to be transferred. Okay. So this is about characteristic impedance, that is Z0 is equal to root over L by C for ultra high frequency lines. Now, impedance relations. Now, to analyze this ultra high frequency lines as a circuit elements, we will consider there are three different cases of impedance relations. Those are given by here. The input impedance depends on the load impedance on the transmission line. Generally, the input impedance calculations depends upon the load impedance as ZL and the transmission line. Right? So impedance relations are of three cases, as three cases are given as, firstly it is said to be open circuited, or lines are called OC lines, and short circuited lines or SC lines. Then when terminated with ZL, means characteristic impedance is terminated with ZL, and when it is terminated with, means when the input impedance is terminated with ZL and it is terminated with Z0. Okay, so there are three cases in the impedance relations. Generally, we are going to consider. One is OC lines, next is SC lines, and followed by when it is input impedance is terminated with ZL. There we are going to calculate input impedance of a transmission line. So open circuited lines, or in short, we'll call it as OC lines, whereas short circuited lines are said to be SC lines. Now, in detail, we are going to analyze the impedance calculations of three cases. The first case, input impedance of open circuited. As the name is given for open circuited lines, those are said to be OC lines. Now, in order to analyze this one, consider one simple transmission line circuit. So, the length of this total length of the transmission line is given by L, and if you are going to analyze, means the circuit is analyzing for the open circuited line. Hence, in the load case, we just assume it as open circuited. So open circuited means that current element which is connected in the load must be equal to 0. So IR is equal to 0, and this is the case the circuit is to be considered as open circuited line. So from this we are going to define input impedance. So to define that, see, input impedance of open circuited line is the line impedance measured as the input of a finite length of line when its far end is open, right? So IR is equal to 0. Whenever there are two terms which are resembles in the circuit, when I is equal to 0, it acts like open circuited. When V equal to 0, it acts like short circuited. That's why in order to analyze this open circuited line, the far end is to be considered as open, hence the lines are said to be open circuited lines. Now, and it is denoted, to calculate whenever this one is considered to be as open circuited, and then impedance associated with that is denoted with ZOC, impedance of open circuited line, open circuited impedance, right? So ZOC, Z is the notation for generally it is impedance, and OC is for open circuited line, right? So in order to write the ZOC equation, see here IR is equal to 0, then based upon that ZL is equal to infinity. Why ZL is equal to infinity? In general, impedance Z is given by, is the ratio of voltage to the current, right? So VR to the IR, generally it is given, and ZR is equal to VR by, according to this open circuited lines, we are assuming here IR is equal to 0. Means if we substitute 0 by here, then something by 0 becomes infinite. This is the case. Load impedance ZL is to be assumed as infinite, right? Now to write the equation for this open circuited lines, now from the voltage and the current relations of a transmission lines, we have been considered VR is equal to Vs source voltage into cos h gamma L minus Is into Z naught sin h gamma L. So this equation part and all how we have been written this one for the voltage and the currents means this equations already we have analyzed in the previous lectures, that is under transmission line equations case. Now VR is equal to Vs into cos h gamma L minus Is into Z naught. Means we are writing for voltage equations, hence all the terms are representing with respect to voltages only. So VR here Vs, and this one is represented with Vs only. Then according to Ohm's law, V equal to IR. Now in place of R here we have Z and I. So all resembles voltages only. Hence VR is equal to Vs into cos h gamma L minus Is into Z naught sin h gamma L. Okay. Then similarly, IR equal to current relation Is is equal to IR equal to Is into cos h gamma L minus Vs by Z naught into sin h gamma L. Now from this, if you want to write the equation for I, then it becomes V by R. Hence in the equation number 2, it is related to KCL, then all the terms are representing with respect to the currents only. Hence, IR is equal to IS, and this is also represents with the currents only. Now, IR equal to IS into cos h gamma L minus Vs by Z naught into sin h gamma L. Okay. So, consider this as equation number 1, and this is number 2. VR and IR relations to be written from the transmission line equations. Okay. To write the equation for open circuited impedance ZOC, see, consider equation number 2. What is there in the equation number 2? That is IR equal to Is into cos h gamma L minus Vs by Z naught into sin h. Okay. So consider equation number 2, that is IR equal to Is into cos h gamma L minus Vs by Z naught into sin h gamma L. Okay. Now in this case, IR equal to means if we substitute IR by 0, then 0 equal to Is cos h gamma L minus Vs by Z naught into sin h gamma L. Now from this, if we equate means separate the two terms separately, then Is cos h gamma L equal to Vs by Z naught into sin h gamma L. Now from this, if we cross multiply these two, Z naught into cos h gamma by L by, if you take this sin h gamma into LHS part, then it becomes in the denominator part as sin h gamma L, which is equal to, and if you take this is into RHS part, then here it will be in the numerator. If you take it into RHS, then it will be in denominator. Hence, Z naught cos h gamma L by sin h gamma L equal to Vs by Is equal to, right? So where Vs by Is is resembles and it is denoted with ZOC, right? So ZOC equal to Z naught into cos by sin. Actually, the formula for sin tan theta is given by here, sin theta by cos theta. And if you take a reverse order of this one, means cos theta by sin theta gives us the reciprocal term to this, is gives us 1 by tan theta, nothing but cot theta, right? So cos h gamma L by sin h gamma L gives us cot h gamma L, right? ZOC equal to Z naught into cot h gamma L, where ZOC equal to Vs by Is. Okay, so this is the way we have evaluated open circuited lines in the presence of UHF lines, ultra high frequency line as circuit elements case. The first case is to be analyzed, that is open circuited impedance ZOC is equal to Z naught into cot H gamma L, where Z naught is said to be characteristic impedance of a transmission line. Next case is, second case is input impedance of short circuited lines. In short, we'll call it as SC lines, short circuited lines. So just now we have seen if the current I is equal to 0 means it acts like a open circuited. When V equal to 0, it acts like short circuited. Hence, the far end is to be considered as short end. That's why VR is equal to 0. In the previous case, we have considered in the OC lines case, their IR is equal to 0. Now it is for SC lines, short circuited lines, hence VR equal to 0. So, see, input impedance of short circuited lines. To analyze this one, input impedance of short circuited line is the impedance measured as the input of a finite length of line when its far end is shorted or shorted with zero resistance. When VR is equal to 0, ZL is equal to 0 and it is denoted by ZSC. Generally, the notation for impedance is Z and SC stands for short circuited. Okay. So previously we have written it as ZOC, that is open circuited impedance. Now it is ZSC, short circuited impedance. So when VR is equal to 0, ZL is equal to 0. As we know that Z is equal to voltage to the current, that is VR to IR. If VR is equal to 0, Z is equal to 0. And that should be considered at the far end, means that that particular place we were being connected this load impedance, hence ZL is equal to 0. Okay. So if ZL is equal to 0, VR equal to 0, and again consider the voltage and current relations of both the transmission line are given by VR equal to Vs cos h gamma L minus Is Z naught sin h gamma L. So here I into R also gives us the voltage term. Similarly, IR equal to Is cos h gamma L minus Vs by Z naught sin h gamma L. Yeah, equation number 2. Now from these two, 1 and 2 equations, we will be considering as, now consider equation number 1, means VR equal to Vs cos h gamma L minus Is into Z naught sin h gamma L. So in that, if we substitute VR by 0, then 0 equal to Vs cos h gamma L minus Is Z naught sin h gamma L, right? So if we equate these two, Vs cos h gamma L equal to Is into Z naught sin h gamma L. From this, if we write Vs by Is is equal to, now how you going to write Z naught into sin h gamma L by cos h gamma L, which is equal to Z naught into tan h gamma L. Okay. So Vs by Is is equal to Z naught into sin h gamma L by cos h gamma L, and here sin theta by cos theta gives us tan theta. Hence, in place of theta, here we'll have h gamma l. Hence, Zs is equal to Z naught tan h gamma l. Right? So, where Zsc is given by Vs by Is, source voltage to the source current, and it is given by Zsc, short circuited impedance, which is equal to Z naught into tan h gamma l. Previously, we have been evaluated the first case as open circuited line, then ZOC is given as Z naught into cot H gamma L. Now ZSC equal to Z naught tan H gamma L. Okay. So in the first two cases, open circuited lines and short circuited lines case, we have been evaluated open circuited impedance and short circuited impedance. Now based upon this relation, we are going to derive the expression for characteristic impedance. Means characteristic impedance in terms of short circuited as well as open circuited lines. Okay. So that can be written as from open circuited and short circuited conditions. As we know that just now we have derived, that is short circuited impedance as Z naught tan H gamma L, and open circuited impedance as Z naught cot H gamma L, which is equal to, see, if you multiply these two, ZSC into ZOC, which is equal to Z naught tan H gamma L into Z naught cot H gamma L. Then Z naught into Z naught becomes Z naught square, and tan theta into cot theta. Means two are representing reciprocal to each other. Means tan theta into this cot theta can be written as 1 by tan theta. Hence, if we substitute this cot theta by 1 by tan theta, both gets cancelled. Answer is equal to 1. Right? So, tan h gamma L and cot h gamma L gets cancelled. Then Z naught into Z naught is multiplied. And the resultant will be Z naught square. Now, from this, Z naught is equal to root over ZSC into ZOC. Right? So, characteristic impedance is given by here under root of multiplication of short circuited and the open circuited impedances. Right? So, this is the way we have been evaluated two cases of ultra high frequency lines as circuit elements case open circuited as well as short circuited. From that, we have been derived the characteristic impedance is nothing but is the product of the square root of multiplication of those two are short circuited impedance and the open circuited impedances. Okay, then next case. Third case is given by here finite length transmission line terminated with ZL. Finite length of the transmission line is terminated with ZL means this is the case we are going to set to be the first condition, important one in the transmission lines part as input impedance of a transmission line. So to calculate that, see firstly length of a transmission line is given by L, and if it is to be extended for this means x is equal to 0 here, x is equal to L is to be considered, and the total length of this will be given as L dash, right? And the load impedance is connected in the output side as ZL, right? And based upon all this impedance assumptions of a transmission line means we are going to derive the equation for input impedance of a transmission line. So finite length transmission line, and it is terminated with load impedance as ZL. So in order to calculate that one, the equation for mathematical equation for the mathematical equation for the uh, input impedance of a transmission line, first we are going to consider the voltage and current relations which are to be expressed some finite length of the transmission line. So the voltage at any location on the transmission line can be written in terms of reflection coefficient as V of L is equal to, where L be the length of the finite length of the transmission line conductor, and V of L is equal to V plus e power j omega t minus gamma L into 1 plus gamma of L. So this can be written as, in general, we know that the solution for the transmission line equations, from that we have written the voltage equation as V plus e power j omega t minus gamma L plus v minus e power j omega t plus gamma L. Now, based upon that reflection coefficient, it is given by a reflected wave to the incident wave means backward traveling wave to the forward traveling wave. That is the case v minus e power j omega t plus gamma L by v plus e power j omega t minus gamma L. If you simplify this one, or based upon this, if you are going to evaluate, then v minus e power j omega t plus gamma L is equal to gamma into v plus e power j omega t minus gamma L. Okay, so in this case, if you substitute v minus by this thing, and if you take in between these two, this term and this term as common, means v equal to v plus e power j omega t minus gamma L plus gamma means v plus into e power j omega t minus gamma L. If you take in between v plus e power j omega t minus gamma L as common, 1 plus gamma is the formula, is left out. So this analysis and all already we have been evaluated in the previous lectures. Now from that I have taken here v of L is equal to v plus e power j omega t minus gamma L into 1 plus gamma of L, where L be the finite length of the transmission line. And consider this as equation number 1. Now the current at any location on the transmission line. So the voltage which we have considered as V of L is equal to this equation, and similarly for current equation means I of L is equal to, as we have derived the previous equation, in the similar way if you are going to evaluate, this equation is given by V plus by Z naught e power j omega t minus gamma L into 1 minus gamma of L. Okay, so if you evaluate V of L and I of L, then those to be considered as equation number 1 and 2. Now I equal to, here also I plus can be written, as we know that according to Ohm's law V equal to IR. From this I is equal to V by IR. Hence V plus by, in place of I plus we just consider, means this is nothing but I plus. I plus e power j omega t minus gamma L into 1 minus gamma L. So I plus into e power j omega t minus gamma L. In place of I plus, we just consider V plus by Z naught. Okay. Then gamma of L is equal to, as we know that if you simplify these two relations, see V minus by V plus into e power j omega t plus gamma L minus j omega t plus gamma L. Minus j omega t plus j omega t gets cancelled. V minus by V plus e power 2 gamma L is left out. So from that we have been gamma of L is equal to V minus by V plus e power 2 gamma L can be written. Okay. So from this we will consider as, see, as L dash is equal to L minus X. Hence the total length of the transmission line is considered to be as and it is subtracted from L dash is equal to L minus X. Now from this L minus L dash is equal to X. Okay. So from this consideration, see, I of L is equal to V plus by Z naught e power j omega t minus gamma L 1 minus gamma of L. Now gamma of X is equal to, so X can be written as V minus by V plus into e power 2 gamma L into this one. Means in place of this gamma L means X, if you substitute L minus L dash, then it becomes V minus by V plus e power 2 gamma X. Generally it is written as gamma of X is equal to, now from this V minus by V plus e power 2 gamma into L minus L dash. Okay, then from this V minus by V plus into e power 2 gamma L into e power minus 2 gamma L dash. See, so that can be written as here, these two separately. So from that gamma of X is equal to V minus by V plus e power 2 gamma L into e power minus 2 gamma L dash. Okay, then from that if gamma of X is equal to, means V minus by V plus into e power minus 2 gamma L dash is replaced by here gamma L into e power minus 2 gamma L. Then Consider this as equation number 3. So gamma L is equal to, as we know that reflection coefficient of a transmission line can be given by here, gamma L is equal to ZL minus Z0 by ZL plus Z0. Right, where ZL is the load impedance and Z0 be the characteristic impedance. Then from that, Z of L is equal to Z0 into 1 plus gamma L by 1 minus gamma of L. Right. So this and all already we have been evaluated. I have taken for a reference as here reflection coefficient of a line gamma L as Z0, ZL minus Z0 by ZL plus Z0, and Z of L is equal to Z0 into 1 plus gamma L by 1 minus gamma L. Right. Now substitute all in one equation, and if you substitute means Z of L by ZL and gamma of L by gamma L, if we consider, then these two are to be considered as Z of L is equal to, previously what we have, Z of L is equal to Z0 into 1 plus gamma L by 1 minus gamma L. So here gamma of L is nothing but this gamma L, and it is given by ZL minus Z0 by ZL plus Z0. Now if you substitute one and in another, means in equation number 4, if you substitute in 5, so number 4 equation, then Z of L is equal to, previously what we have, Z of L is equal to Z0 into 1 plus gamma L by 1 minus gamma of L. In place of this gamma of L, if you substitute Z minus Z0 by ZL plus Z0, then this becomes Z of L is equal to Z0 into 1 plus gamma of L. Nothing but ZL minus Z0 by ZL plus Z0, right? And gamma of L means, previously what we have gamma of L, this one, and in place of this gamma of L, if you substitute, means gamma of X is nothing but gamma L means into e power minus 2 gamma L. If you substitute gamma L by, that is ZL minus Z0 by ZL plus Z0 into e power minus 2 gamma L, then it becomes, see, ZL minus Z0 by ZL plus Z0 into e power minus 2 gamma L by 1 minus gamma of L, means ZL minus Z0 by ZL plus Z0 into e power minus 2 gamma L. Okay. Now if you simplify these two equations, means we analyze this equation, Z of L is equal to Z0 into, in the numerator, if you take ZL plus Z0 as LCM, then ZL plus Z0 into plus ZL minus Z0 into e power minus 2 gamma L by ZL plus Z0. In the similarly, in the denominator part also, if we take ZL plus Z0 as LCM, then this becomes ZL plus Z0 into minus ZL minus Z0 into e power minus 2 gamma L. Right? So if you observe, in the numerator, this is the relation, and in the denominator, this is the relation. In both sides, this ZL plus Z0, ZL plus Z0 gets cancelled, then Z of L is equal to Z0 into ZL plus Z0 plus ZL minus Z0 into e power minus 2 gamma L by ZL plus Z0 minus ZL minus Z0 into e power minus 2 gamma L. Okay, so that can be written as here like this, Z of L is equal to Z0 into ZL plus Z0 by ZL plus ZL minus Z0 into e power minus 2 gamma L by ZL plus Z0 minus ZL minus Z0 into e power minus 2 gamma L, where gamma be the propagation constant, ZL is load impedance, and Z0 be the characteristic impedance. Now, in order to simplify this equation, we are going to multiply the total denominator and numerator term with e power gamma L. Okay, so now it becomes, if you multiply e power gamma L, then Z0 into first term ZL plus Z0 into e power gamma L plus ZL minus Z0 into e power minus 2 gamma L into e power gamma L by ZL plus Z0 into e power gamma L minus ZL minus Z naught into e power minus 2 gamma L into e power gamma L. See, e power minus 2 gamma L, e power gamma L. Actually, there is a formula that is a power m into a power n is equal to a power m plus n. Means here e power minus 2 gamma L into e power gamma L means e power 2 gamma L plus gamma L. Then it becomes e power minus gamma L. Okay. So then z of L is equal to z naught into zl plus z naught e power gamma L plus zl minus z naught into e power minus gamma L by zl plus z naught into e power gamma L minus zl minus z naught into e power minus gamma L. Right? So in order to simplify further, we just consider here. See, z of L is equal to z naught into e power gamma L means in between two. See previously what we have. Now z of L is equal to, that is z of L is equal to z naught into zl minus z naught into e power gamma L plus zl minus z naught e power minus gamma L by zl plus z naught into e power gamma L minus zl minus z naught into e power minus gamma L. See, zl plus z naught, so same. So now from this, if you separate ZL e power gamma L and e power minus gamma L, or if you take ZL and Z naught terms as separately, then Z naught into, in the numerator, if you take first ZL as common, so ZL is multiplied with e power gamma L, and here is plus e power minus gamma L. Then plus Z naught. If you take Z naught as common, e power gamma L minus e power minus gamma L. Right? And similarly in the denominator also, if you take ZL as common, then e power gamma L minus e power minus gamma L, then plus, if you take Z naught as common, e power gamma L, then plus e power minus gamma L. Okay. So now based upon this one, so that equation is to be considered as Z of L is equal to Z naught into ZL e power gamma L plus e power minus gamma L plus Z naught into e power gamma L minus e power minus gamma L by ZL into e power gamma L minus e power minus gamma L plus, if we take Z naught as common, e power gamma L plus e power minus gamma L. So that should be written as here Z of L is equal to the total thing. Now based upon that, now to simplify further, we just consider, since e power gamma L plus e power minus gamma L by 2 is the formula for cos h gamma L. Similarly, e power gamma L minus e power minus gamma L by 2 is for sin h gamma L, where h is for hyperbolic functions. Okay. Now, if we substitute in place of 2, e power gamma L plus e power minus gamma L by 2 as cos h gamma L, e power gamma L minus e power minus gamma L by 2 is for sin h gamma L, then these two becomes, see, z of L is equal to z naught zl cos h gamma L plus z naught sin h gamma L, and by zl sin h gamma L plus z naught cos h gamma L. See here, minus term means this is sin and this is cos. Similarly, here it is cos and this is sin. Okay, that's why cos sin, sin, cos. So let z of L is equal to z in. Z of L is nothing but input impedance of a transmission line, that is Z in. So Z in is equal to Z naught. Means consider this as the relation, and from this Z naught into, if we take here ZL and means cos h gamma L as common in the numerator. See, cos h gamma L as common in the numerator, then it becomes ZL plus Z naught into sin h gamma L by cos h gamma L in the denominator, that is, again if we take cos h gamma L as common in the denominator also, then ZL into sin h gamma L by cos h gamma L plus Z naught is common, right? So in the numerator and denominator, these two gets cancelled, which is equal to Z naught into ZL plus Z naught. Sin theta by cos theta, nothing but tan theta, that is tan H gamma L by Z naught plus ZL tan H gamma L. Okay, see, Z in is equal to Z naught into ZL plus Z naught tan H gamma L by Z naught plus ZL tan H gamma L. So this is the equation for input impedance of a transmission line for lossy. Why? Because gamma is exist means alpha is also exist. As gamma equal to alpha plus j beta, then gamma is exist means alpha is also exist. Where alpha exist means attenuation must be there. Attenuation means loss must be there. Hence it is said to be lossy transmission line input impedance equation. To get lossless, we must equate means alpha equal to 0. Then from that, we'll be see here. For a lossless line means, as we know that for a lossless line, gamma attenuation constant alpha equal to 0, then propagation constant gamma equal to j beta only. As we know that propagation constant gamma for a transmission line equation, gamma equal to root over r plus j omega L into g plus j omega c. If we take like this, now if we consider for a lossless lines means r equal to g equal to 0, then j omega L into j omega c is left out, which is equal to j omega root over LC, where gamma is nothing but alpha plus j beta, which is equal to j omega into root LC. Now if we compare both sides, real and imaginary, where real term alpha equal to 0, imaginary term beta equal to omega root over LC. As alpha equal to 0, there is no attenuation there is no amplitude reduction in the signal, hence that line is said to be lossless transmission line. So for a lossless transmission line, alpha equal to 0, gamma is nothing but j beta. Hence, tan h j beta L. Previously in the numerator term, we have a numerator as well as denominator. Tan h gamma L is there. If we substitute this tan h gamma by tan h j beta L, then formula becomes j tan beta L. Right? Tan h j beta L is equal to j tan beta L. Right? So if we substitute this j tan beta L in that particular equation, then Zin is equal to Z naught into ZL plus Z naught tan h j beta L by Z naught plus ZL tan h j beta L. Right? So tan h j beta L is nothing but j tan beta L. Hence Z naught into ZL plus j z naught tan beta L by Z naught plus j zl tan beta L. Okay, this is the equation for input impedance of a lossless transmission line. Lossless transmission line input impedance. That is Zin is equal to Z naught into ZL plus JZ naught tan beta L by Z naught plus JZL tan beta L is called as input impedance of a lossless transmission line. So in this lecture, we have analyzed three cases of a input impedance. That is, first one is ultra high frequency lines we have seen. So basically the frequency range of this ultra high frequency lines, UHF lines or RF lines, will be 300 megahertz to 3 gigahertz. At very high frequencies, Z naught can be written as root of L by C. Right? Now from this means the ultra high frequency lines can be acts as circuit elements for the transmission lines as inductance and the capacitance. Now from that there are three cases of impedance variations we have considered. One is ZOC, open circuited lines, and the second one is short circuited lines. So from that we have been calculated ZOC as Z naught cot H gamma L and input impedance of short circuited impedance of SC lines as Z naught tan H gamma L. Now from this we have been evaluated Z naught is equal to root over ZSC into ZOC. Now third case of this impedance variations as lossy transmission line input impedance and followed by lossless transmission line input impedance. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.